Good afternoon, everyone.
Good afternoon.
Uh, what do you all see on the screen right now? Do you see it in like a full screen mode or
In your PowerPoint mode.
yeah, the slideshow mode?
No, it's not slideshow.
It's not slideshow mode yet. Okay. Let me try.
Much better.
How about now?
Yep, good.
Oh, okay. I think we'll wait for another few minutes and then we can start.
So Yogesh, your list of what you intend to do, is that up to date?
That's right. Yes, that needs to be updated. So last week, actually, the 6th and the 7th, we continued with the neural network and CNN for the week 7th. Today, we will be covering the K-means clustering. But you're right, we got to fill up the description and the respective Coursera topic and the hands-on ML columns. And
So,
I got to as well upload the last week's YouTube video. So
so the SVN will be later. That's correct.
right, we did not cover the SVM last time. We continued with the neural network, so that also got to be updated as well.
It's obviously a topic I'm interested in.
The which one?
The SVN, I'd like to learn more about that, but
Oh, okay.
it's a good topic. Thank you.
Okay. I think we can get started here. Welcome everyone. Today is our 8th week, so almost 2 months into this AI seminar. So today we will be covering the K-means clustering. It will be fairly short lecture compared. I don't think I'll run more than 60 minutes over. So fairly short lecture in that case. We'll be covering the K-means clustering. Last week we covered last 2 weeks we covered the neural network and uh, convolution neural network by Brian. So this week we will touch upon the clustering, which was remaining. So it is the unsupervised learning algorithm, and next week we will probably touch base with the reinforcement learning algorithms and imitation learning, I believe. So one of the two. So that would be covered by Brian as well. So So for today's class, we will use slides from the Engineering, the Coursera ML course. The lecture 13 of that is dedicated to the K-means clustering. So just to recap, like in a supervised learning, what we have is we have a set of labels associated with an input data set. So we have like an X and Y, X. So in this case, we have like X1 and X2, and the data set already represent whether these points over here are circle or these points over here are cross. So they are already labeled. So that's the supervised learning. So in that the data set, we have the input features and the output features. So by label, I mean the output features. So whether it's a square, rectangle, and so on. Um, so that would be the supervised learning. And in supervised learning, you could use something like neural network for classification technique. So that would be the supervised learning. And in an unsupervised learning, what happens is we only have a data points associated. So we just have input feature set, which, so in this case, we have like two features, X1 and X2, and the two features have distinct values associated with it. Now, there is no labeling. So by that, what I mean is there is no identification whether these are circle or a cross. So like what we have in this. So the data set would already have that, say 1 by 1 would correspond to a circle, or 2 by 2 would correspond to a circle, and this coordinate would correspond to a cross. So that's the label. Whereas in unsupervised, we don't know to what category does it belong to. And that's the task of the clustering algorithm, is to figure out what are the different distinct categories that are in a given data set. So that in this illustrative example, there are two, but you may want to divide this further. Like you could have these three data points belonging to one cluster. These two could be belonging to one. These 6 or 5 points may belong to another cluster. So it just depends on the application domain and the domain knowledge that you have into deciding how many clusters that you are really interested from that given data set. So that would fall under the unsupervised learning. So what are the different applications of, so I think we covered this in one of our intro classes, but basically the clustering is used in a lot of different domains. So in web commerce or like like user studies kind of application, you might be interested in figuring out like what is your user base interested in. So for instance, if you are a retailer and if you have a list of prospective buyers, then you might want to figure out like whether that prospective buyer um, is having a relatively high probability that he is going to buy, or is he just interested in looking at what are the items that are available in the store, for instance. So you might have some more insights with respect to that buyer, say his income, uh, which locality, and so on and so forth. And based on that, you might be able to come up with a segmentation or a categorization for that particular or that individual buyer, whether he falls in one category or the other category. So that is one use case of clustering. There are also use cases like organizing computing clusters. So for this, there might be scenarios wherein if you are running like a cluster, an HPC cluster, for instance, you might be running a lot of unknown applications in your cluster. If you are um, uh, an HPC admin, then you might be interested in finding out like which are the applications that are very compute intensive, like, or you might be interested in figuring out like which are the applications that take relatively long time to execute a given computation, or you might be interested in knowing like what are the simulations that take a very long time or the short time. Uh, in that scenario, there is no labeling associated with it. And the only data that is available with you is perhaps how much the CPU utilization of that given application is, or how much is the RAM utilization of given application is, and perhaps how long that application lasted, right? And based on that information, you might then want to cluster the different kinds of application into different categories. So in one category, you could say that it is a very compute intensive application. Perhaps other category could be like it is a very short-lived application because it ran only for a few seconds and so on. So those are some of the insights you might be able to gather once you run some kind of a clustering algorithms. So that's one. And there are also applications which I'm not familiar with, like astronomical data analysis and social network analysis. So those are some of the applications domains. Are there any, is anyone in the audience using one of the clustering techniques in their projects and might want to perhaps share like what domain that they might be using it? Okay, but yeah, so let's move on to the next. So in this, we will be talking about K-means clustering. So let's look into how the K-means clustering algorithm works. So you have a data points, like all these green dots that you see on the screen are like different data points and they have different coordinates. And if I had to make a call is like, how can I categorize these data points into some category? So one possibility is like I could have all these data points belonging to one category and all these data points belonging to another category, right? So that's one possible approach. Another possible approach could be we could cluster all these lower half points into one category. Then you could have all these points belonging to one category. Um, Perhaps you can also divide these points into this category and the rest of the points into another. So we basically have like 4 clusters over here. But that's all this is what we can achieve visually looking, right? But you might have a very large data set and you would want to have some automated program or algorithm that does that for us. So in K-means clustering, it tries to create clusters based on a given data set. So in this particular example, suppose we know that there are just 2 clusters. So in K-means, what it does is you first have to tell the algorithm that we are interested in finding 2 clusters in this whole data set. So the way the clustering works over here is it first randomly points, selects 2 points in this space. Okay, so one is a blue cross and one is a red cross. So these 2 points are selected as cluster centroids. Okay, so these are this is our initial random guess. Okay, so after this, what happens is from these centroids, okay, the cluster centroid, we figure out which are the points that are closest to this center, to the centroid. So for example, you have this point over here, right? So what we do is we first measure a distance between this green dot and this red, okay? And then we also measure a distance between this green dot and the blue one. And based on whichever has the shortest distance, um, that point is associated with that particular cluster centroid. Okay. Similarly, this pattern is repeated for all of these points in the space. So here you can see that after the first iteration, what has happened is all these points over here, since they have the shortest distance to this compared to the blue one, all these points were labeled as red, okay? And all these points on the right-hand side, since they were closer to the blue cross, they were labeled as blue dots. So next, what we have, the clustering algorithm does is, now that we have identified what are the different dots and the clusters, right? What it does, it tries to figure out what is the mean of all these points. And so what is the centroid of all these points, basically, okay? And based on that mean or the average, this particular centroid is moved to that new centroid, okay? And then the same process is continued. So let's see what happens next over here. So based on this new data set, it determined that this would be the new centroid for this particular cluster. Similarly, for the blue one, the new centroid should be somewhere over here, and that's what it has identified. Now, so now that we have identified, we have first, so here you can see there are basically two steps. First is associating a point with a cluster, and the next step is finding a new centroid for the cluster. So these are the two steps that iteratively and repeatedly happen until some optimization or the cost is satisfied, or basically it finds the minimum cost for this whole optimization problem. So over here, it just does the same. So once previously it had identified this, now it tries to figure out based on these new points. So you can see, like, from the previous iteration, all these points were belonging to red, right? Even this guy was belonging to this red centroid. But when, this centroid. But when we made a new centroid over here, the distance between this point and the new centroid, and the distance between this and the new centroid over here, the relative distance was, this one was closer to this point, and that's why it kind of shifted to a different cluster, the cluster blue in this case. So basically, you just keep on repeating the same iteration, finding out the new centroid, and then associating all the points that belong to that centroid. And yeah, and I think this is one of the final steps. Once you keep on running the iteration, at some point you reach a minima wherein you have a center, you have identified or clustered the input data sets into two different clusters. So that's just an illustration of how this K-means clustering works. So this just puts it to the mathematical form. So you have an input data set, and for this K-means cluster, you have to specify how many clusters that you want, and that is defined by K. So in our previous case over here, the K was 2. So that's why we had 2 clusters. So that's what you have to supply to this algorithm, is how many clusters that you want, and the training data set. And not going to go too deep in this, but basically what it says is, in the first step over here, it does the cluster assignment. So by cluster assignment, we basically kind of associate a dot or a point with a given cluster centroid. Okay. And the next step is we got to move the centroid based on the mean distance for that given cluster. So that's what the gist of this step is. And the optimization objective over here is given by some of the squares of the centroid and each of the points. So as long as we reach the minima for this cost function, um, the loop exits. So that repetition loop exits, and we have kind of found out a minima at which basically we have clear distinction between what points are associated with which category or the cluster. So the next thing is, in our previous example, we just said that we have a value of k which we knew that we want to set it to 2, right? But that not necessarily be the case depending on the applications that you are using. So so how to best guess what would be the value of k is will be dependent on the application domain that one is using. But there is a way to figure out what would be a good amount of categories or clusters that one can find in a given input data set. So let's look at how one can achieve that. So there is something called as an elbow method. So in an elbow method, what you can see is as you keep on increasing the number of the value of k. So in our previous scenario, we had k equals 2, right? But say we want k equals 3, right? And then at that point, we might have certain cost function. And if you keep on increasing the cost function, you will see that, or let's look at this figure. So if you keep on increasing the number of clusters, there would come an instance wherein you won't see significant improvement in the cost function. So over here, you can see when the k equals 2, the value of cost function was very high. But when the k equals 3, there was a drastic gain in this cost function. Okay. And if you further keep on increasing the value of k to 4, you'll see that there is marginal improvement in the cost function. And as you keep on increasing the clusters, the gain that you see is marginal. So it's just a trade-off as to what you want to select the cluster. You can keep on increasing the cluster, but the cost function would, as you can see, that there's not a lot of gain that you would get by increasing the clusters. So this is what they call an elbow method. Now, this is, as I mentioned, with respect to the application domain. So over here, it just depends on the application, how many clusters you want. So perhaps you might be, so in this figure you see, there is a t-shirt size, and you can see that there is a corresponding height and a weight associated. And these are the manufacturer is basically trying to figure out what should be the label of the t-shirt is going to be, and what is the height and the weight to which that t-shirt will basically fit. So the manufacturer might be interested in finding out like what are the ranges of the height and the weight for, say, 3 different categories of the t-shirt label, right? So if he runs through that a clustering algorithm and says that the k value has to be 3, then the clustering will come up with 3 such clusters, and for each of the clusters, he she can then find out what is the range of the height and the weight associated with those clusters and then do the appropriate marketing of that. Similarly, the manufacturer might be also interested in like not just having three kinds of t-shirts, but having even finer granularity of that labeling, like XS, S, M, L, XL, and so on and so forth. So he could perhaps come up with a clustering scheme wherein the K is say 5 or 8 and so on. And based on that, one will be able to associate it, the range of the height and the weight for that given specification of that t-shirt. So that's just an example. Um, so with respect to finding out the optimal number of clusters, there is another method called silhouette method. So in that, um, it tries to come up with a score value, and that score is usually ranges from -1 to 1, and the score which is closer to 1 is a better approximation, and it gives you a good idea as to whether that the cluster, the number of clusters that we have identified for a given data set is better or not. So this is one automated approach one can leverage from the scikit-learn library, but there are I'm sure it's also there in other Python libraries or R libraries, and it will let you know like what would be an optimal number of clusters for a given data set. So that's something one could leverage if you don't have a knowledge of how many clusters one can build from a given data set. So let's look at some of the use cases. So I think that covers the slide portion, and I'm gonna share. Let's see. Okay, I'm gonna show a couple of Jupyter examples. So this Jupyter notebook is hosted on Kaggle. So that's, as you all are familiar by now, it's a website wherein there are a lot of data sets and competitions for machine learning. So in this particular example, it uses k-means clustering to identify like what are the neighborhoods that are there in a given city. So in this particular example, it's a New York taxi data set. So that's one data set which has information about like what was the coordinates of a pickup point for a passenger, or what are the coordinates of a drop-off point for a passenger, the date of the week, duration, and it has a lot of other information as well. But for the purpose of this particular example, we will just limit to the pickup points. And let's see. So if we look at the data set, so it has like input, longitude, pickup, latitude, drop-off, latitude, longitude. And if we try to visualize that on a map, then it will look something like this, right? Now, if you are a taxi operator, okay, if you are like an Uber, for instance, then you might be interested in finding out like what are the different neighborhoods that are there in this given now that we know what is the data set look like, what is the pickup demand, and what are the passenger demands, and so on. The operator, for instance, like Uber, might be interested in placing their taxis at certain neighborhoods, right? So how can they figure out that? So one way is using the clustering, and what they could do is basically, given this data set and the input features like the passenger drop off, pick off, pickup, and so on. It can figure out what are the different neighborhoods that are there that can be clustered. And based on how much demand there is for a given neighborhood and so on, it can do the taxi scheduling kind of. So over here, it has found like it has labels for these 10 neighborhoods, and they have just tried to portray it over here. Okay, no clustering at this point. It's just kind of trying to overlay what are the neighborhoods that are there on this map. Um, and then it tries to it tries to run the k-means clustering, and it says that we just want to have 10 neighborhoods, and so the value of k over here would be the 10, right? And based on that, it comes up with some pickup latitude and longitude, and what is the cluster centroid for that cluster. So you can see that there are 10 clusters, and these would be the different neighborhood names, right? And if you try to portray that and associate all the pickup points to the different kinds of neighborhoods, then you could see something like this visualization. Uh, is this thing visible to everyone?
Yes, it is.
Okay, thank you. So that's just one example use case of clustering. The second use case, which is there, is to figure out the customer segmentation. So there is this data set which has like information about a customer, like what is their score, the purchasing power, what is their salary, and so on. Again, so it uses something called mall customer.csv, which is a part of this input, right? And it has like customer ID, gender, age, annual income, spending score. I don't know what that is, but that's another field over here. And based on this, it basically, for this k-means clustering, it just uses two features, the annual income and the spending score. And based on these two features, it tries to identify the different groups in this customers. So here you can see that that elbow method that I was talking about. You can see that there is a, as you keep on increasing the number of clusters, um, this is the index or the inertia that they call. So there is a way so to find out that inertia is there is k-means dot inertia, and that will give you this value over here, and that you can plot, and you can see that for 3 it is high and 4 it is lower over here, right? So perhaps the 4 would be a good cluster size for this data set. Yeah, I think they have chosen 5 because it's even further down. So yeah. And based on that, you can now group the different individuals based on what cluster that they would belong to. And this is just a visualization of that. And here you can see the user has then tried to identify like, okay, the red color is belonging to earning high but spending less. So those are the different categories of users that it has come up with. Right? Yeah, this is similar. This is kind of the same data set, but just a different visualization. So here it has shown some distribution of the customers based on different age and so on. So that's just showing like the different features of the Python library, right, for the visualization sake. Yeah, so that's what here it tries to plot, and that's the code for that. All right, so another example, I think this, I think this is also similar. Let me see, what's this? Yeah, this is about the iris data set. So yeah, so this Jupyter notebook basically goes through that iris data set, and here one says that we would like to have 3 clusters. Okay, so you can see in that iris data set, it already has the species name associated with it. But if we ignore this species label, which is our predicted output, for instance, if we ignore that and let the machine learning identify us the different categories, then it will perhaps come up with some kind of, using the k-means, it will try to co-locate or categorize the different input data sets into the 3 different species. And this is just showing the centroids and the different categories of the flower data set. Yeah, let me see this final one. This is leveraging the k-means clustering on a handwritten data set. So as we had covered in one of the class, if we have all these points, all these numbers that are written, and we don't have any labels associated with it, right? So for instance, initially, if somebody tries to write all these, so he might write 8, 2, 9, and so on, but we don't know uh, to which number this input belongs to. So whenever somebody writes a number, we don't know to which, what that number represents, and we want a machine to figure that out for us in an automated way. Then perhaps what we could do is, given this input data set, we could say that um, group all these digits into 10 different clusters, because we have 10 different numbers. So 0, 1, 2, 3, all the way till 9. So we have like 10 distinct numbers. So just take this input data set and run a k-means clustering with k equals 10 and try to group all these input data sets. So that's what it is trying to do over here, is it takes that input data set, runs through that reshaping function, right? Um, and it runs through the clustering algorithm, and then it just associates all these digits or these numbers into what label it may belong to. So it just uh, categorizes all these input points or the input digits into the different numbers. And the inferred label over here is basically somebody has labeled that particular cluster with that name. So this is an external label. It is not a label that is generated by the algorithm. So just to make it clear. So yeah, so that's, and here you can see that it shows a frequency count on that. So if 0 is, there's just uh, one instance wherein there was a 0 image available. There was like 1018 times the 2-digit was identified, and so on. So it just shows all that. And yeah, here it just it has, yeah, I think that's that. And let's look. I think I covered what I had in mind to cover for today's class. So these are some of the inputs that I'm interested in. I'd like to hear from you all. Is like, what are the topics that you would like to see to be covered in the coming class? So if you all have any suggestions or anything particularly that you might want to learn more about. Also, like, are there any projects or ideas that perhaps you might want to volunteer and give like a 5-10 minutes intro about? So that is also welcome. And any ML work and any ML work that uh, you are currently involved in your project that you all want to share. So any inputs on either of these topics from you all? Okay, I know Mary wanted SVM to be covered. How about others? Dan, Purvodai, Himanshu, Daniel.
I didn't have anything else in particular. Himanshu might have something in mind, maybe some image recognition for like, I mean, just a practical example, like, I don't know, license plates or something like that.
That will be really great if we can, come up with, find a sample data set and do a full run-on-the-mill example with it. So I described a bit earlier in the email, right?
Yes. I think that would be a good example. So I think the example that Himanshu is mentioning is about car data set. And if there was a use case wherein, or if there was some implementation wherein we could categorize the cars figures based on what model that car belongs to just by looking at that figure. So that's one good use case that Himanshu suggested that we could cover in the class. Any other topics or something that you all would be interested in, so that we can seek out whoever is working on those topics and have them covered during these lectures, even though we might not be familiar with those topics. So any inputs are welcome on that.
So currently what we covered are very basic things. In the real world applications, sometimes, many times actually, this learning enabled systems operate in the real field where you are constantly getting updates in the real life situations. And so you have to be able to relearn your system so that you can continue and apply the learned policy in the updated world. And so there is always a time constraint on how fast you could relearn. There is a time budget, and maybe there may already be some example directly available for that. That might be something interesting for folks who are trying to use it in the real world.
Mm-hmm. Yes. Any specific application, like a software architecture or something that perhaps anybody would be interested in? Like, for instance, one could run some of these models like in scikit, right? But what if the data set is very large, right? So in that case, you might not be able to fit everything in one compute node. So in that kind of scenarios, some of the frameworks like Spark or Hadoop or those kind of things might be a good use case for doing all these large scale learning. So anybody interested in any of those aspects?
Oh, absolutely. I think that's a fantastic thing to add, because as soon as somebody takes what they learned and try to apply it in for some real world setting, they will run into these problems. And without this resolution using Spark and Hadoop, there is no solution. So I think that will be really good addition.
So do you have stuff that you're talking about with TensorFlow as well?
Pardon? Could you repeat that, please?
TensorFlow and then GPUs? Discussion about any issues around that?
So I personally don't have much experience with TensorFlow, but I believe Brian has worked on PyTorch with and TensorFlow through
If,
the
if we can compare some of those, because I know on the AA program we're using, but they've used PyTorch in the past, but they're using TensorFlow and Keras.
right, right.
I'm
Uh,
interested in why and look, contrast them maybe.
mhm. So, would it be useful for you, for example, say running one of the k-means or neural network? So to just compare scikit implementation, TensorFlow implementation, Keras implementation. Is that something would
That would
be
be good.
appealing?
Yeah, because then you get a chance to understand why you would choose one of the others.
Okay,
I would
okay,
include PyTorch in that as well.
right, right. Okay, yeah, that's a very good point. Let me just write that down. Yeah. Okay. Yeah, we can certainly include in one of the classes just dedicated to some of these questions over here.
And that way people, I mean, I know people use what they're familiar with, but that gets them thinking about considering other options too for the system.
Correct, correct. So I have just noted the PyTorch, scikit, those comparison, the car image, and perhaps Spark execution of machine learning models. So
And also, how do you incorporate real world updates into a machine learning component within a available budget?
can you talk about available budget? What do you mean by that?
So in the real life situation, you may have to, you may have only limited amount of time, right?
Okay,
So with the new changes that comes in, you suddenly
right.
have to relearn and learn a new policy and apply it within a limited time.
Okay. Do you have any specific machine learning models that you would be interested in?
So like you can say deep reinforcement learning.
Right. So that, so yeah, I think that would be the reinforcement learning.
Yeah,
Okay. So relearning in scenarios of reinforcement learning.
yeah, right.
Okay. Not necessarily the neural network or this, because reinforcement learning is another. I think that would be covered in the next class.
Okay.
But uh, just to make sure, because like the neural network, machine learning, and all this, these are like an offline kind of way, right? Reinforcement learning that we'll cover in the next class is mostly going to be an online learning of a model.
Right, right.
Okay. Okay.
And this is a question for Daniel. So, most of the time when we design some learning enabled component or use neural networks or other, SVM or other things, we are basically looking at the problem using our background knowledge of what it takes to use machine learning for this particular application and try to design some kind of method to solve this. Uh, so it's mostly reliant on the mindset of the data scientist and how he's looking at the data, what the problem is, and try to figure out a particular algorithm that will work in this particular situation. I'm wondering if there is more, is there any work where somebody has done something which is more systematic? So, a more systematic way of creating machine learning algorithms, applications for a particular problem.
There probably is. I'm not that aware of it. I haven't looked into it, but I do know as of a few years ago, there was this keynote by the former director of the DARPA I2O, John Launchbury, and he was talking about his learning enabled systems, and at least then, and it probably still holds. He said when you talk to people and you'd say, look at this neural net. Why'd you pick 4 layers here? Or why'd you pick 5 layers? And
Right.
well, we tried 4, then we tried 5, it didn't improve, so we went with 4. There was no, it was still just as much of a magic and as art as it was of a science. And I think that's still the case. I'm sure there's work to try to make it more systematic, like you said. I'm just not that aware of it. And if that's coming down from the head of DARPA I2O, then it's probably still the case that there's a lot of black magic involved.
Well, yeah, in case you find anything recent work in this area, that will be very applicable for ISIS, because we do model-based software development and WebGME and everything, and so we can immediately build upon that.
Right. Yeah, I agree. Okay, I'll keep an eye out for that too.
Cool. Thanks.
Okay. Any final comments before we end this week's lecture?
No.
Okay. If not, I will upload the slides on this GitHub repository. Just star it, watch it, or whatever. Keep an eye on that. Just a reminder, we will also include the video recordings of every week, and they would be also linked to this GitHub page. So next week we will have the reinforcement learning. Ignore the week number over here, but next week we'll have the reinforcement learning, which I think Brian is going to be covering, and I'm hoping he will have some of the open AI gym kind of facilities that is part of that reinforcement learning toolkit and so on. So yeah, it would be an interesting lecture as well. So thank you, everyone. See you all next week.
Thanks, Yogesh.
Thank you.
Bye.
Bye.